Hello everyone, in this video we're going to see the solutions to Worksheet 1 in sections 2.1, 2.2, 2.3, and 2.5. So the first exercise is an exercise in limit, and is one of those limits where we might not get a numerical value. So if you notice here, we have limit when x goes to 0 of 3 over x minus 3 over x squared plus 2. This is going to a number, 3 over 2, but this is going to something like infinity. And we're getting like infinity minus a number. So we want to check and see if we can disregard this piece and just classify this as an infinite limit. So to do that, we're going to use subtraction of fractions. So we have p over q plus or minus r over s. We get that this is p times s plus or minus q times r over q times s. So we can see this as limit when x goes to 0 of 3 times x squared plus 2 minus 3x over x times x squared plus 2. Notice that we have now a single fraction, and single fraction we can classify if it goes to infinite or if it goes to minus infinite more easily. This is going to be the same that having 3x squared minus x plus 2 divided by x over x squared plus 2. I cannot factor this into something that's going to cancel out x, and because I cannot do that, then I'm not going to be able to fix the fact that this is going to 0 below. But if you check the top is going to 6, positive 6. So this is going to a positive number, and below is going to 0. So this means that overall, this goes to infinity. So if the bottom approximates 0, and then you have that something is approaching positive number, and the top this goes to infinity. If it's approaching a negative number, it goes to minus infinity. Okay, and this is something that we're going to see much more in limit at infinity and infinite limits in the next week. Now let's go to exercise number 2. So for this question we have two functions, f and g, and f and g have different behaviors, and they have points where they're not defined, their limits do not exist. And so that's going to influence what happens here with these different limits that we wanted to try out. Notice that, for example, for any operation, we have that the operation exists, the limit of the operation exists, if and only if the individual limit exists. So, for example, here we have limit when x goes to minus 1 of f of x plus limit when x goes to minus 1 of g of x. And this will be fine, and this will exist if and only if each of the individual limit exists. But as you notice, minus 1 is a specific point where both in f and in g, the limit do not exist. Why? Because the limit on the right side is different from the limit on the left side. When we're approaching minus 1, this side gives me 2, this side gives me 1, and for g, when I'm approaching minus 1, this side gives me minus 1, this side gives me minus 2. So overall, this do not exist. In b, we have a similar situation. Although the limit when x goes to 2 of g exists, notice that this will normally be limit when x goes to 2 of f times limit when x goes to 2 of g. And yeah, the second one is this, isn't 0. This function is going to 0 here, but this function here does not have a limit. And so this is a do not exist situation, and because this limit do not exist, then overall the multiplication is not going to exist. When I take lateral limits, when I'm only checking for the left side or the right side, then things change a little bit. So for this one, I'm going to find out first where is the limit when x goes to 1 by the right side of g. And the limit by the right side of g of going to 1 is going to be minus 1, right? And so what this means is that c is going to be equivalent to the limit when y goes to minus 1 of f of y. That's what I'm trying to figure out here. this becomes this, and again, I'm approaching by the right side, so this is going to be by the right side as well. And so when I'm approaching by the right side here to -1, this is going to be 1. So this will be producing this 1 over here. Now if I'm going by the left side, limit when x goes to 1 by the left over here of g, then this will be 2 over here. And so this limit here with the limit when y approaches by the right side 2 of f of y. And if approaching 2, well, it turns out that in this scenario it's not going to exist. Oh, sorry, I'm approaching by the right side, so this is going to approach and it's going to be 1. We got to be careful here between if we're approaching just a single side or if we're approaching the general limit. Now for the limit when x goes to 3 by the right side, we check first what is the limit when x goes to 3 the left side. This is the left side of g of x. And 3 by the left side of g of x is going to 1. We're approaching by the left side to 3, it gives me 1 over here. And so this becomes the limit when I'm approaching 1 by the left side of f of y. And when I'm approaching 1 here by the left side, this is giving me 2. So first I find out what is 3 by the left side, then it gives me 1, so that is what is the approach to 1 by the left side, and that's going to give me 2 here. Now for this quotient, I need to find out what is the limit when x goes to 2 by the left side of f and g, right? And if this limit exists, then the limit of the quotient is going to exist. 2 by the left side here of f is actually going to be 1. And 2 by the left side here of g is going to go to 0. So this is going to 0. So this is positive and this is going to 0. So overall, the quotient is going to infinity. It's something positive or over something that it goes to 0. So it could be called to infinity. But also we can say that because g of 0, so according to the rules, if g of the point does not exist, then simply we can just say that the limit overall do not exist. Okay, because the rule says the limit of the quotient only exists if g of this point is different from 0, but this point is approaching 0. Now, by the right side, we're going to have the same issue. This is approaching to 0 as well. So, and this is approaching to f of when approaching to by the right side. This is approaching here a negative value. So I can call it do not exist. Okay, or I could also consider that is eventually going to go to minus infinity. Now, in general, the limit this when x goes to 2 is not going to exist, right? Because of this reason that I mentioned, that when we're going on one side is going to infinity, and by the other side is going to minus infinity, right? This is going to 1, and below is going to 0. So this is approximating. It's not like I can divide 1 over 0. So 1 over 0, it goes to infinity. And here, it will be minus 1 over 0. And so this is like it goes to minus infinity. They're going to two different directions. So I cannot even think that they're going to be infinity at all. It's just the limit is not going to exist. And that's perfectly alienated with the rule that f of 2 is 0, so the limit of the quotient cannot exist. Okay? individually, if I think of it individually, if I think, well, what is g of 2 when we're approaching by the left side, what is g of 2 when we're approaching by the right side, then we can kind of get away with say, well, this is like 1 going towards here, so this is infinity positive, infinity negative, but in general is going to not exist. Okay. Now, another limit that showcases that well is this limit here, limit when x goes to 1 by the left side of x plus 2 times x minus 3 over x minus 1. Notice that I know that if I'm approaching one of the sides, then this is just going to go towards certain infinity. But I want to know what is the sign that this is approaching. And so the best way that you can take this exercise is just to check with some values. And so let me pull out the Desmos. This is something that you can do. So Desmos calculator. And I'm just going to plug the function that we have over here. F of x equals x plus 2, x minus 3, and then everything divided x minus 1. And so now I'm going to make a table. You can kind of see the graph even in here. So you can kind of see what's going to happen when we're approaching minus 1. By the left side, you see that this is going to infinity. So you can kind of see that this is what's going to happen. We're going to get that the limit is infinity because this is like growing out to infinity here. Well, let's check this out with some points. So I'm going to check this by f of x1. And so now I have a table here. So because I'm approaching 1 by the left side, I'm going to take 0.9, then 0.99, then 0.99, and I keep increasing. And so notice that if I continue increasing, the number starts getting really, really large. First is 60, then 600, then 60,000, and then it's a lot more. And if I continue going, then this is gonna get a gigantic number over here. So this is going to infinity. This is what I can tell from here. Okay. Normally that's what you do, and you'll also draw like a table here, right? You can do x, f of x, and then you can check the values over here just to check where it's going. This is exactly the situation in what I just made here. So this is what you want to do in these situations. You want to explore with some numerical values where this is going. Now, exercise 4 here is find the equation to the secant line to the graph f of x, x cubed minus 2x plus 1 that goes through the point x equals minus 1 and x equals 2. So you got to remember that the slope of the secant line is pretty much given by the intersection of those 2 points. So you do f of 2 minus f of minus 1 over 2 minus minus 1. And so that's going to give me the slope that crosses towards those 2 points. Again, I can use something like the calculator or whatever to just try and calculate those points. Now I'm going to change here my f to be this x cubed minus 2x plus 1. And I'm just doing this right now with calculator, but you can do this pretty much by hand. You can just plug the numbers, right? So this is going to give me 5, and this is going to give me 2. And you can kind of see it here. If you plug 2 to the 3, this is 8. minus 2 times 2 is 4 plus 1. So this is what you get here. A minus 4 plus 1 is 5. And if you plug minus 1 in here, you get minus 1, then plus 2, then plus 1. And you have right here the 2 plus 1, 3. And so this is 5 minus 2 divided by 3. And so this is 3 over 3. This is 1. Right? And that coincides with the values that we're getting here, 5 and 2. Okay? But this is something that you can do by hand. So if you're doing an exam that you cannot use calculator, you can still do this by hand. Okay, now once that you have the slope, you got to remember that the equation of the line is only y minus f of certain value, or y minus a y0 equals mx minus x0. And the y0 can be anything here. So for example, we can pick the f of 2 can be y0. So y minus 5 equals 1 x minus 2. And this will be the tangent line here. The secant line, sorry. Y equals x minus 2 and then plus 5. Moving this 5 to the other side. So this is y x plus 3. And that will be the equation of the line. Now, exercise 5 is about understanding what is the meaning of what the slope of the secant line is, and what the slope of the tangent line is. And so the secant, m of the secant line, is just pretty much p of 100 minus p of 50 over 100 minus 50. And we really don't need to know what this is in terms of the function. We don't need to know. We just know that this is the change on the population over a certain change in years, right? So change in years. So this will be, this secant line is represented as the change in population between 1950, right, and the year 2000. This is what it means, because it starts at the 1900. So P of 50 is 1950, and at x equals 100 is 100 years more. So the year 2000. So the secant line represents the change in the population between these 2 years. Now the slope of the tangent line is different. The tangent line here is when we're approaching x equals 100. So this is the limit when x goes to 100 of p of x minus p of 100 over x minus 100. So it's similar to the quotient that we have over here, but we're taking this limit. And what this means is the change on the population at exactly the point at the year 2000, which is 100 years later. So this is something between two different dates, and this is an instantaneous point. This is at the point x equals 100 or the year 2000. And this is just what it means. This is a differentiation between the tangent line and the secant line. Now, some of these exercises here are a little bit about understanding what certain trigonometric values can mean, and also about using the logarithmic and exponential function. So for example, if we're doing here this expansion, what you want to do with this is you want to use the properties of the log. And so notice that this is the log of a quotient. The log of a quotient is the log of the top minus the bottom. So this log of this quotient becomes the log of this minus the log of this. Okay. Now we have each of the individuals. The next property that we can use is the product here. The product is the sum. So this is log of sine power to the tangent plus log of x minus 4 power to the 5 minus log of x plus 2 to the cosine of x. And the next property that we can use is that we can put the exponents in front of the log. So this is tangent of x, log of sine of x, plus 5 log of x minus 4 minus cosine log of x plus 2. And hopefully all this formula sounds familiar. If they do not, then you gotta remember a little bit what the properties of the log are. So log of a over b is log of a minus log of b. Log of x to the n is n ln of x, and the log of the product is the sum of the logs. So this is what you're trying to remember here, to recall here. And now the next is a little bit of reminder of what the trigonometric functions are and how they function. So the 6 trigonometric functions are, of course, sine, cosine, tangent. And the first thing that you got to remember is, well, let's find out what is sine of 5 pi over 6. And then you can say, well, if I remember correctly, this is like minus sine of 5 pi over 6. And you might have in your mind a little bit of what the unit circle was. If not, that's something that is worth checking out, the unit circle. And for special angles, how much are you going to get for particular values? So in this scenario, 5 pi over 6, we have that the sine is going to be 1/2. So by the minus in front, this is going to produce minus 1/2. Now, in terms of the cosine is going to be square root of 3 over 2. So the cosine, and the cosine of a negative is pretty much the same as the cosine of a positive. So this cosine here, it doesn't matter. This is 5 pi over 6. And this is a square root of 3 over 2. And this is, again, you should remember some of your special angles on the unit circle. So if this sounds alien to you, then go back and try to look for special angles on the unit circle. Then you go for tangent of 5 pi minus 5 pi over 6. But once that you have sine and cosine, you have everything, because then you can just do tangent is supposed to be sine over cosine. So once that you have sine and cosine, you have everything. And this is like minus 1/2. And this is the square root of 3 over 2. And so you can cancel this out. And this is minus 1 over square root of 3. Now cotangent here of minus 5 pi over 6 will be either cosine over sine, right? So this is cos over sine. And so you're flipping around these values here. So square root of 3 over 2 over minus 1/2. And so this will be minus the square root of 3. Secant is 1 over cosine, right? And so this means 1 over square root of 3 over 2. So this is 2 over square root of 3. And cosecant is 1 over sine. And so that'll be pretty much minus 2. And remember, of course, I'm using the same angle here. I'm not writing this out, but this is 5 pi over 6. And this is sine of 5 pi over 6. So this is just a reminder of how to use these trigonometric values. Now, another question that is a reminder here from this worksheet is also how to solve this equation 3 to the 2x plus 1 equals 8. Now, notice that there are different ways that you can approach this out, but the most simple situation that you can do is just use a natural log on both sides. And so you have 3 to the 2x plus 1. And you have here log of 8. There's no way that I can simplify this with common bases. This is just going to be that. And so I get 2x plus 1 times log of 3 equals log of 8. And then I have 2x plus 1 equals log of 8 over log of 3. And so now 2x is log of 8 over log of 3 plus 1. And x is the whole thing, but divided by 2. Okay? And so this is just for solving the equation. The trigonometric equation is a reminder of how to do this type of things. Hopefully you remember this from your pre-calculus. Now, exercise 9 is a little bit more about how to compute limits that are a little bit unusual. And we have the limit when x goes to 0 of x squared plus 4 minus 2 over x squared. One of the things that you notice is that if you plug right away 0, this is going to give you 0 over 0. And so this is not good. And I need to do something to flip around this and to find out the real limit. So what happens is that I'm going to use a technique that is called multiplying by the conjugate. And so I'm going to leave this same thing here. And then what I'm going to do is, usually I'm going to have a difference, some sort of difference here. And so I'm going to multiply by the same term of the difference, but now I'm going to change the sign. So here's going to be plus 2. And same thing up and down, so I don't change how things are happening. So because I have this, then, well, what am I really using is the difference of squares, which is a minus b times a plus b is equals a squared minus b squared. So now this becomes square root of x plus 2 plus 4 squared minus 2 squared, which is 4, right? And this is limit when x goes to 0 at this, and x times x squared plus 4 plus 2. Now notice that the square root is going to cancel out with the square. And so that is going to provide me a limit when x goes to 0 of x squared plus 4 minus 4. And here, notice I can cancel now the 4 with the 4. And I'm going to have, and this is x squared. And I'm going to have limit when x goes to 0 of x squared over x squared square root of x squared plus 4 plus 2. And now I can cancel the x squared. So now my limit is not anymore a 0 under 0 situation. but this is 1 over x square root of x squared plus 4 plus 2. And now I can plug in 0 without issues, and this becomes 1 over square root of 4 plus 2. And so the square root of 4 is 2, so this becomes 1 over 2 plus 2. And so this is 1 over 4. And the overall limit here is going to be 1 over 4. So this is a very complex algebraic limit. Now the last part of this worksheet was, if I know that I have a function that is between two different things, for what values of a, the squeeze theorem is going to help me calculate this. And what happens is that I want to check out where these values are going to be equals. I want to find out where the limit of the squeeze theorem tells me that the limit when x goes to a for x minus 9 should be equal to the limit where x goes to a of x squared minus 4x plus 7, right? So I need to find out what are those points where that happens. And if those two limits are true, then in, let's say there's a certain number L, then the limit when x goes to a of f of x is also going to be L. And that's what the squeeze theorem tells me. But essentially what we're saying is, well, and so if these two limits has to be equals, then 4a minus 9 gotta be equals to a squared minus 4a plus 7. So I'm establishing an equation that is going to give me certain values for which this is going to function. So I'm going to fold this in a single thing. So I'm going to move this 4a to the other side. And notice that now is going to becomes a squared minus 8a. And this 9 is going to go to the other side to add. And so it's going to become 16. And so notice that I can factor this out. This is a binomial square. This is a minus 4 square. This is the binomial a minus 4 square. The first one is square is a square. Twice the first one by the second is a. And 4 squared is 16. So this function. And so this is only going to have a solution when a is equals to 4. So pretty much a equals 4 is the only value that is going to work out for the squeeze theorem here, where these two things are going to be equal. All right, so this was exercise number 10. Now, but last but not least, we have exercise 11, where we're trying to check for continuity. And we're trying to find out what are the possible values that makes these functions continuous. Now, by definition of continuity, you need to have that the limit when x goes to c of f of x must be f of c. Okay? But the meaning of that is that the lateral limits, they must exist and they must be the same that the definition. This is telling me that f of 9 is 6. So we're here gonna find out where the continuity is going to happen for x equals 9. So I can change this here for 9. So instead of using c, now I'm gonna be using 9. And I want this to happen. Okay. So first, then I need to figure out how to make the limit when x goes to 9 to assist. And I have x plus c here, right? And I have a square root of x minus 3. So if I plug this right away, then this is going to cancel out and it's going to give me a 0 down below. So what I'm going to do is I'm going to make a difference of the squares here. And that's going to tell me pretty much what's the c that I need. Turns out that this is the limit when x goes to 9. And I can factor this out as a difference of the squares as the square root of x minus the square root of c times the square root of x plus the square root of c. Right? And I want to eliminate this down here. So to be able to eliminate this one with this one, then what happens is that c needs to be 3. And so let's find out if that's actually true. So let's assume that c is equals 3. Then this limit becomes limit when x goes to 9 of x squared root of x plus 3. And what's going to happen there is that when I plug the 9, this becomes 3. Square root of 9 is 3. 3 plus 3 is 6. So this actually becomes 6. And it's going to be equals to f of 9. So indeed, the value that's going to make sense here is going to be when c is equals 3. Okay. All right, so that's the end of worksheet number 1. We have some weird exercises here that you could learn something about it. Remember, from all the worksheets, you're only supposed to work a couple exercises and see how you do. And these tend to be hard exercises. So don't get too hung up if you didn't get exactly my solution. The important thing is that you learn something out of these difficult exercises.